And all right, so I think it's good that we spent a lot of time on questions, and you know, it's the point here is not to necessarily finish every single slide and rapid fire at you, just like in the first lecture. The point is that you take something home from this and you learn at least a concept. You know, you might, for the specialists in the audience, of course, the equations might be more interesting, but I also want to convey some of the physical and conceptual ideas of how things generally work and function and jiggle about and you know, how fun the quantum world is. All right, so let's get back to the main part of this, which is what we do with the transmon qubit. We have now broken up the transmon very neatly into a linear piece and a nonlinear piece. Let me expand the nonlinear piece, and let's try to look at what happens, assuming that this fluctuations phi ZPF are very small. Right, quantum fluctuations are usually small, so it makes sense we should say they're small. And if you remember, what that corresponds to is the width of the lowest energy state, which will come here. If we make those fluctuations very large, then that ground state, right, if we make those 0-point quantum fluctuations very, very large, then that ground state will look really funny in here. And you notice that some weird stuff will happen, that it will start to leak into nearby regions. So we don't necessarily want to do that. So let's look at this fourth order term. Okay, so if I just look at the nonlinearity, it looks like negative EJ, and then we have, let's zoom in a bit. We have negative EJ, phi ZPF to the fourth power. This is really just some constant, so I'm not even going to worry about it. I'm just going to leave it aside and focus on A plus A dagger to the fourth power. And here I'll drop the hats for notational simplicity for the moment, so that I can write a little quicker. So if I expand this part of, and I said I'll drop the hats, so let's drop them. If I expand this term, you notice, of course, that we have just 4 copies of the exact same ladder creation and annihilation operators. If you multiply these out, you can see that a lot of terms will pop up, such as, for instance, let's start with the first one. So we have A, then we can have A dagger, then we can have plus A dagger A plus etc. Right? So there's quite a few terms. There's a rather large multiplicity. Now we're going to do a very important and convenient trick, which is that every time we see a term such as, let's take this term for instance. Let's take the term which is A dagger A. A term that has a lowering operator on the left side of a raising operator. We're going to move the raising operator over to the left. And the reason for that is that if you remember, A applied to a Fock state N produces a very simple result. And if we can write everything in terms of products of A dagger to some power M, A to some power N, called normal order, we can very quickly and easily evaluate the expression applied onto a state such as this. So let me give you an example here. Suppose we have exactly this term which goes like A dagger, A. We can use the commutation relationships between A and A dagger, which commute to exactly 1. They're scaled precisely to have this very nice and easy relationship. Oops. This is the commutator. We can use repetitively the fact that A dagger is equal to 1 plus A dagger A. And so substituting this expression back into here, and apologize for the extra long red line there. Let's do that Substituting that back in there and just focusing for the moment on this term, we can replace AA dagger with A dagger A plus 1 times AA. Now you notice what has happened is that a 4-body term, AA dagger AA, this is a, if you want, we like to call that 4-wave mixing. This 4-wave mixing term has now produced 2 terms. It has produced a term that goes like A dagger AAA, or in other words, A dagger A cubed, plus another term which is just AA, which is A squared. And so we've broken up a 4-body interaction into 2 pieces. A piece that is again a 4-body interaction that it has ignored the commutation relationships that you can get purely classically, and a term that would not exist in classical physics or in classical considerations that came purely from the non-commutativity of these operators. So this is a non-classical term, right? Whereas this is just the 4-wave mixing. Now, you might be wondering, why do I call these wave and wave mixings? Well, recall from the first lecture, or from the beginning of this lecture, that in phase space, if I write the operator phi and q here, and I look at alpha, the trajectory of the oscillator, simply rotates in a circle like this. And the rotation as a function of time of alpha, let's maybe write it up here, this evolution is governed by alpha of t is equal to alpha of some initial condition e to the negative I omega naught t, where omega naught is the frequency of the linear oscillator. In the quantum case, we similarly had that a hat of t, which is the Heisenberg picture evolution of the bosonic operator, is equal to a hat in the Schrödinger picture, or a hat at time 0 if you want, times e to the minus I omega naught t. Again, this kind of semi-classical correspondence. Now we can use this type of picture analysis to think of these operators up here as waves that rotate, right? They have some amplitude, A, and they rotate at a particular frequency, e to the I omega naught. You'll also notice that if we dagger one of these operators, then we dagger the initial operator here, and we complex conjugate the exponential. In other words, A rotates to the left, and A dagger rotates to the right. So it represents motion in the opposite direction. If I substitute this dynamic picture back into the equations above for the terms, you notice the terms that look like, say, A dagger A cubed in this picture will combine to say A dagger e to the plus I omega naught t times A cubed e to the negative 3I omega naught t, which we can then say is equal to A dagger A cubed, and then we can combine the two oscillations into e to the negative 2I omega naught t. So you notice that this term remains oscillatory at the frequency 2I omega naught t, or at the frequency, sorry, omega naught, 2 omega naught. Now consider a term that looks different, a term that looks like this, A dagger squared A squared. Again, these are all the possible terms that can come from the expansion of the fourth power of A plus A dagger, which seems Simple enough, but you'll notice that it creates every possible combination between A and A dagger, and with some multiplicity. Right. So let me just focus now on another term in order to isolate the different kinds of behaviors you can have. Well, this term, if you think of it in this picture, looks like A hat, let's redraw that, looks like A dagger, e to the plus I omega naught t squared times A e to the minus I omega naught t squared. And so this looks like the mixing of two waves, A dagger squared, A squared, times e to the plus 2I omega naught t, e to the minus 2I omega naught t. And you'll notice that there's an interference here, an interference which precisely cancels out the rotation of the dagger with the A dagger. And so this term is stationary. This term doesn't oscillate in this picture. And so I can write this out as A dagger squared, A squared. And so we can classify these terms into two categories, terms that do oscillate and terms that don't oscillate. And so I'll highlight this in a green color to indicate that this term, contrary to, say, the one that doesn't have an equal number of A daggers and A's, this is a non-rotating term, whereas the one above is a rotating term. Now, you might be starting to wonder, why am I trying to identify rotating and non-rotating terms? And that's going to be along the lines of pushing us into a very important approximation called the rotating wave approximation, something you covered in lab yesterday. And that approximation will say that, well, if I have a Hamiltonian which has terms that are stationary, or maybe I should just write this as some h naught, which does not depend on time, plus some plus a Hamiltonian that is rotating at some time, at some interval t, to a first approximation. Again, this is just an approximation that works well if I assume that this oscillation here is very fast and the amplitude of h rotating is very small, to a first approximation. I can say that this Hamiltonian is approximately equal to just h naught. I can essentially drop all the rotating terms. And I think Nick might have covered this in more, should have covered this in more detail in yesterday's lecture. Now, I know we've kind of jumped into very few specific terms, so let me go back to the lecture and back out and look at how does this term expand and what are all the expansions. So if you sit down and perform exactly what we just did, which is to take all of the possible combinations of the expansion of a plus a dagger to the fourth power, you get a zoo of terms. And the zoo of terms comes into first two flavors. The first are four-body mixing terms, which I've highlighted here in purple. Right? And these are the terms that you would obtain classically. And also you get all the terms that result from the commutation of A and A dagger. And these are terms that appear strictly because of the non-commutativity of these two amplitudes. Because of the non-commutativity of these two amplitudes, you also get some more zero-point fluctuation terms, but this is a constant stationary energy term, so we can always just drop that. Now notice that we can further subdivide these terms into two pieces. Pieces that oscillate at frequencies, say, 2 omega naught, and pieces that oscillate at frequencies negative 2 omega naught, and pieces that don't oscillate, these that are stationary. That similarly holds here. This A dagger to the 4 term in the Heisenberg picture will oscillate at a frequency of, say, 4 omega naught, or minus 4 omega naught. This term will oscillate at negative 3 omega naught, 2 omega naught. This term here will oscillate at no frequency. In other words, it doesn't oscillate. It's a stationary term. And of course, this term will oscillate at 2 omega naught, and this term will oscillate at just 4 omega naught. The frequency omega is just given by the difference in the number of creation versus number of annihilation operators. And so what we can now say is, to very much in the same way you did in your lab, we can approximate, let's run this, we can approximate all the terms that, do the rotating wave approximation, which is equivalent to first order perturbation theory, and to remove all the oscillating terms. Again, using the idea that the ladder operator rotates at this very particular frequency. So if we simplify this Hamiltonian now, dropping all those terms, it reduces to something beautifully simple. We get 2 contributions. We get a contribution that we recognize from the harmonic oscillator part. That's just the harmonic approximation. We get a term that looks like the harmonic oscillator energy that's quadratic in energy, where it's bilinear, it's A dagger A. That comes exactly strictly from the nonlinearity, and a term that is a 4-body or a 4-wave mixing term that is new, that is nonlinear. We haven't seen this term yet. This will be crucial. And so if we move down to this line, the second term is due to the nonlinearity. The first one is due to this piece here, this delta Q, is due to the commutation relationships that arise from the nonlinearity. Now, what are these alpha and Q? I've simply taken the coefficients from the line above and defined h bar delta Q to be actually the same value as h bar alpha here. And that equals 1/2 the Josephson junction energy times the 0-point quantum fluctuations of the reduced magnetic flux to the 4th power. Okay, and this is a crucial relationship because on the left what we have is the renormalization of the linear frequency of the oscillator due to the 0-point quantum fluctuations, right? The way we can interpret the term over here on the left is that this piece only exists because A and A dagger don't commute, which represents the quantum 0-point fluctuations, and the amplitude of this term is exactly dictated by the size of the nonlinearity times the amount of fluctuations of the mode. Now, because it's a nonlinear mode, when it fluctuates, the fluctuation activates the nonlinearity. So as the ground state is fluctuating, and some of the times it's sort of, if you want, climbs up here, that climbing up to a higher energy, up to a higher potential, allows it to explore the nonlinearity at a higher level. And so that, in effect, then dresses the frequency of the qubit because the particle is experiencing a softer opening, right? This energy landscape here opens up, the cosine opens up relative to the quadratic, and so it lowers the frequency. The second term here is the Kerr term, and that's going to be very crucial, as we'll see in the next slide. So I can rewrite the equation from the previous slide using the notation n is A dagger A, where n is the photon number operator. So it says how many Fock states of the classical harmonic oscillator do I have in 2 pieces. The first piece is using omega q, and which I'll define as the dressed frequency of the qubits. So it's omega naught, that's the frequency of the linear part of the qubit minus delta q, where delta q is the lamp shift or the dressing of the frequency by the nonlinearity, and h nonlinear, it's the nonlinear piece of this. Now the beautiful thing is that we know the eigenstates of the linear piece from the harmonic oscillator, our favorite bread and butter ingredient. This nonlinear piece has a very interesting effect in that the nonlinear piece goes like n times n minus 1. And to first order, it's dispersive. It doesn't change the eigenstates. So maybe for the slightly more familiar with this with quantum physics, if you apply first order perturbation theory, the energy change to h lin due to h non-lin, the nonlinear piece, is calculated by the overlap between the eigenstates of h lin, or h0 in this case, and that will be a correction given by this term, which we can also identify easily because we can write n times n minus 1 applied on the Fock state n is equal to n, the number of excitations, times n minus 1 times the Fock state n, right? And that's because n hat is equal to a dagger a. Now, if you're wondering how did I jump in the previous slide from a term that is in the form of a dagger squared a squared to this term here, that's by, again, using the commutation relationships, but in the reverse order. Right, so we can write this term out as follows. Using the commutation relationships, I can, again, reverse the term and swap it out so as to allow us to get the a dagger there. Now, the more important piece is that the eigenstates of the harmonic oscillator, which I'll label here as K0, this is the expression for the perturbation theory for the change in the eigenstate, say K0 of the simple harmonic oscillator, which are the eigenstates of h lin, how those are affected by the nonlinearity. This is the first order correction. It's given by how h nonlinear links one Fock level, maybe n, to another Fock level, maybe m. And you notice that because the composition of h nonlinear is only a dagger a terms, a dagger a, doesn't link a dagger a is only non-zero in the case where n and n, the two states it links, are the same. So to first order perturbation theory, the eigenstates don't change. And that you can also visually see in saying that, well, to first order, this purple curve and this brown curve are basically the same. It's only when you go to higher excitation or higher order that the two curves really look different. Right, so we can rewrite the energy within the rotating wave approximation of the transmon to fourth order in the power expansion for Fock states, like this. And so what does this physically begin to look like? Well, we can see that, let's look at some experimental parameters. So here's a device that I designed and measured some time ago, and it has the following real parameters. The capacitance between this pad and this pad, which maybe we can write like this, is very small. It's 65 femtofarads. It's a pretty small number, but very typical for these kinds of devices. And then the inductance associated with this nonlinear inductor, the Josephson tunnel junction here, this inductance has a value of 14 nanohenries. Again, a very small inductance in the grand scheme of things. Now, these correspond to a Josephson junction energy of about 12 gigahertz. And maybe for the expert in the audience, this is a so-called charging energy, the energy associated with the charge, the position, the momentum variable is about 0.3 gigahertz. So if we now look at how the eigenstates of the oscillator look like to first order, we can plot the oscillator eigenstates, familiar to us from the first lecture, here, where the wave function of the ground state as a function of magnetic flux phi is depicted here. Again, it has a mean position of 0, and it has a width, a standard deviation of phi ZPF. This amazing, very often appearing parameter. Of course, then this is the one excited state, two excited states, and so forth. Now, our approximation breaks down as you get to very high states. You notice that the harmonic oscillator eigenfunction for the fourth Fock state here is bounded within the parabola and not within the cosine, so these eigenstates are much more heavily renormalized. But again, our interest is in the qubits, so we're going to really almost exclusively focus on what's happening down here at the bottom between these two levels. And you notice that the energy difference, the splitting between the ground and first excited level, and for this qubit, is exactly about 5 gigahertz. This was by design. However, the energy difference between the next two levels, and alpha here is the change, sorry, so I guess maybe the way that I should really write this is that the difference between the energy of the second level and the energy of the first level is equal to omega qubit minus alpha. Whereas the difference between the energy of the first level and the energy of the ground level is equal to omega qubit. And this is precisely what we set out at the very beginning of our talk yesterday, that we wanted an anharmonic level diagram, a level diagram where the levels are not equally spaced. And so we have finally shown from the beginning, from almost first principles, how you obtain this anharmonicity, this non-equal spacing between the first two levels and the second two levels. And the extra anharmonicity here is about 0.3 gigahertz relative to 5 gigahertz. So it's about a 10-ish% correction. Yesterday someone asked, well, what is the impedance value of these oscillators typically, or of this transmon? So for this transmon, you notice that it's about 450 ohms. So it's relatively large, because this is an impedance measured at 5.3 gigahertz, and it's very difficult to get above a kilo ohm. To first order, of course, the eigenstates haven't changed. Now, if we look at the zero-point fluctuations, which I alluded to earlier, the zero-point quantum fluctuations of the charge that corresponds to these real parameters, very much for a device like the one you might measure in your Qiskit experiments, are about 1 Cooper pair, or 2 electrons. So in the ground state, there is about exactly 1 Cooper pair worth of charge kind of fluctuating, if you want, back and forth from one island to the other island. And then the magnetic flux is oscillating at the level of about half a magnetic flux quantum. So very much in the same way that 2 electrons is the scale, is a fundamental scale for charge, the magnetic flux quantum, if you remember, phi naught was Planck's constant reduced divided by 2e. This is the scale for flux. And that one electron is a very small number because, again, there are about 10 to the 12 mobile electrons in each side of this transmon qubit. So you can see why we have to work at very, very cold temperatures, right? This explains in part why the environment must be very pristine, why we hope that things are very isolated from noise, because think about it, our fluctuations of the ground state are 1 Cooper pair, the fluctuations of the excited state are roughly 2 Cooper pairs, and to distinguish that we need to have the noise not swamp 1 out of 10 to the 12. That's a very minute number. But amazingly, this macroscopic effect is highly robust, and we've been able to engineer these systems within the community to be able to work with these systems almost as if they're isolated, ideal, real atoms. What does the energy level diagram look like a bit more explicitly of this transmon qubit, and what are the experimental signatures you might see? So again, let's look at the Fock levels, or the energy eigenstates. So this is the ground state, let's say here. Then this might be the excited state, 1. Then I'll exaggerate here and draw the second excited state, 2, like this. And I see that we can do that. Right, and then the energy of the ground state, let's just label it as 0. The energy of the first excited state we'll label as h bar omega q. The energy of the second excited state is h bar omega q minus alpha. And so when you drive a qubit, when you control a qubit, you tend to drive transitions at this frequency, omega q. And you notice that that frequency is very, very different from the frequency required to transition to the second level, either from the ground or the first, which is omega q minus alpha. However, it doesn't mean that if you start in the ground state and you now excite yourself to the first excited state here, it doesn't mean that you can't suddenly apply another frequency tone at this lower frequency, which can allow you to then hop from this latter level to the next. Or to use 2 photons to excite from the bottom level of the ground state using 2 quanta of energy that combine and take you from 0 directly to 2. Now that process is very difficult in the sense of it's not very likely to occur. You need to drive with a ton of photon and put in a lot of power, because photons don't like to combine in a way, but it's possible to occur. And so what you would experimentally measure in an experiment and resolve spectroscopically is to say that as a function of the frequency that I probe at, I might see a transition line in the spectrum that appears at a frequency here. And unfortunately, I seem to have erased my diagram. So we can recreate these energy levels very quickly. That appears at a frequency omega q that corresponds to the transition between the ground state and the first excited state. So this would be omega 01, which I'll call omega qubit. And this I'll call omega 01. This we'll call omega 02, or it's omega qubit minus alpha. And then you might see another peak which appears slightly lower in frequency, spaced by about a difference of alpha, the anharmonicity of the transmon. And this is the difference between 1 and 2. And you can also potentially see a peak that looks like the difference between the second and third, and so forth. So these are experimental signatures you can observe in, say, Qiskit Pulse or in your demo lab at home. Oh, and I think we have covered that yesterday, so that's a reminder that the annihilation, creation, and hopping operators have these relationships. And the reason that I'd like to now remind us of that is that we have just explained that using frequency, we can now isolate the qubit in this frequency range. What that means is that if we only apply control or pulses or frequencies of our drives that try to steer the atom by force, in this range we can really isolate the 0-1 transition, and we can isolate the qubit as 0 and 1. Now if you remember what the creation and annihilation operators look like, we can therefore restrict ourselves to operate within a manifold of the lowest 2 energy states. And so the photon number operator, A dagger A, which looks like this, and my notation here means that this let's take the term 2. This term of the matrix corresponds to an operator that takes the state 1 and maps it to the state 1 with amplitude 2. That's what my notation here represents. This, let's say, matrix element here would take the state 3, it would take the state 3 and map it to the state 1. So this is where it comes in, this is where it goes out, with amplitude 0. So it's 0. I'd like to just indicate the basis of that these matrices are written, and you can always, of course, swap the basis, but it's important to keep track what you use. And because of the anchronicity, alpha, which is roughly 10% of the frequency, is about an order of magnitude, we can restrict ourselves to just the lowest two states, 0 and 1, and therefore restrict all of our operators of the Hamiltonian, photon creation, the annihilation operator, to work just in the qubit subspace. And that's what allows us to then identify that the first part of the Hamiltonian here, the photon creation operator, minus some arbitrary shift, overall shift, restricts ourselves exactly to the qubit Pauli sigma z operator. And of course, our favorite ladder operator A becomes the annihilation, the fermionic annihilation, or excuse me, I shouldn't call it fermionic, the two-state restricted annihilation operator, or the Pauli lowering operator, sigma minus, which is a combination of the qubit Pauli x minus I qubit Pauli y. So these are, of course, the matrix representations. So we've just taken a leap from an oscillator to a spin. And I hope that reminds you of the picture of slide in the first part of the talk, where I think I mentioned there are only two types of physicists, and maybe you can see which one I tend to be most of the time.